Hello, my name is Derek, and today I'll be presenting my Lab 2 project on projectile motion. In this experiment, I used both Tracker and VPython to study the motion of a ball launched in 2 dimensions. The goal was to compare how our different models, one with air resistance and one without, matched the real-world motion. The purpose of this lab was to investigate how a projectile behaves when launched horizontally, both with and without air resistance. I collected experimental data using a video tracking and built 2 computational models in VPython. By comparing those results, I was able to evaluate how accurate each model was and which physics principle best explained this motion. This lab is based on Newton's second law, F net equals ma. In the simulation, gravity is modeled by Fg, which is equal to negative mg. Drag force is modeled by Fd is equal to minus b velocity, proportional to velocity. I use numerical integration to step forward in time, constantly updating velocity and position using these forces. The model without drag produced a clean, symmetrical parabolic path, which is what we expect from the idea of projectile motion. When drag was added though, the peak height and the range both decreased. This behavior closely matched what I observed in Tracker, where the projectile didn't travel as far as the no drag model predicted. I used a 20-gram ball and threw it horizontally from a height of 0.6 meters from the island. The motion was recorded using my phone camera and analyzed using Tracker. I marked a calibration point using a meter stick and tracked the ball's position frame by frame to get the x and y and the trajectory data. This data served as experimental reference for validating my VPython models. The VPython simulation used a loop that updated the ball's position and velocity every 0.001 second. In the no-drag model, the net force was just gravity, which meant F net is equal to vector 0 negative the negative mass of the ball times g, comma 0. That's the vector. And in the drag model, I added a force proportional to velocity. So force drag was equal to negative b times the ball's velocity. So F net would be the vector 0, comma mass of the ball times g, comma 0 plus force of drag. And this is what allowed me to simulate how air resistance gradually slows the ball down in both x and the y direction. Here are the tracker results. The red dot shows the measured x and y position over time. The x versus t curve is not perfectly linear, which indicates drag is slightly slowing the ball down. The y versus t curve shows the parabolic descent, matching the theoretical models expected. In this plot, you can see the output of the model that includes drag. The projectile has a shorter range and a lower peak height as expected. This matches the tracker data much better than the model without drag. The velocity vectors also shrink over time, showing energy loss due to air resistance. This slide shows the no-drag model. The trajectory is symmetric and smooth, a textbook's parabola. However, it overestimates both the range and the peak height because it doesn't account for any showing forces. This model is accurate in ideal conditions, but in less realistic for the real-world motion, like what we captured using Tracker. When comparing all three, the Tracker, with drag and no drag, we see that the with drag model most closely follows the experimental data. The no drag model overshoots in both time and distance. This reinforces the importance of including air resistance in realistic simulations of projectile motion. Some of the errors included were the drag coefficient B was estimated, not measured, so it wasn't very accurate. Manual tracking introduces small measurement errors as well, especially for fast-moving frames, and the tracker frame rate may have introduced timing inaccuracies too. To summarize, the no-drag model is useful but oversimplified. The drag model better matches real-world data both in shape and scale, and including air resistance is crucial to simulate motion accurately in Earth's atmosphere. So, finally, a what if. What if there was no gravity? Then the object would continue moving in a straight line at a constant velocity according to Newton's first law.